Okay, Thermal 1 class, let's get rolling here. I threw the schedule up one more time just to kind of see where we are. This is the 22nd, and so this is the second of the lectures from chapter 6. And then we have one more next Tuesday, and then we have Opportunity Day, as my old prof used to call it, on the 29th. I have been working on the test. I currently have about 10 problems. Yeah, they're pretty short. It could morph into 11 or 12, or I have to sit down and take it. I've worked them all. I haven't taken it at one sitting to see how long it takes me to work through it. I figure if I can do it in 45 or 50 minutes, it ought to be fair. So it could be up to 12, maybe not. I'll give you more insight on Tuesday. But they're multiple choice, work the problem. You get it right, you match an answer, click the answer, and off you go. Okay, so with that, let's go ahead. We've got a lot of material to cover today. Okay, so we are back into talking about entropy. We covered the entropy discussion for control mass last time, and so now we're going to extend to control volumes. We just pick up the mass flow terms, and everything else stays pretty much the same that we've already described. So I guess like mass and energy, entropy can be transferred into or out of the control volume by streams of matter. So last time, for the control mass, what did we have? We had a way you could increase or decrease entropy in the system was by heat transfer, right? We could increase the entropy if we had heat coming in. We could decrease the entropy of the system if we had heat coming out. So that was a plus or minus. And then we had the production term, which we can actually manufacture, irreversibilities manufacture entropy. And so if we had dissipative effects, friction, turbulence, whatever inside that control mass, that was going to produce entropy. And that term could only be at best zero or positive. It could not be negative because you cannot destroy entropy. You can transfer it in and out, but you can't destroy it. Okay, so now we're going to go extend the discussion to control volumes, and so now we're going to have streams of matter, mass flows into and out of the control volume, and they will carry entropy either into or out of the control volume with them. So since this is the principal difference, the flow of mass between a closed system and a control volume or an open system, in terms of entropy rate balances, the control volume form can be obtained by simply adding those mass transfer terms to the closed system equation that we had before in order to account for the entropy transfer. So basically, we take the same equation that we had. On the left, we've got the transient term. If there is a rate of change, rate of entropy change, evaluate, that's ds cv dt, evaluated at some particular time t, and that has to equal all of these other terms. And so we've got the heat transfer term, the summation over J of all of the heat transfers coming in divided by the temperature on the boundary at which that heat transfer occurs, okay? So, usually it breaks down into we're putting it in on the top, taking it out on the bottom, something like that. Maybe we've got a stray on the side. We have an amount, and then we have a temperature on the boundary, and we simply take that heat transfer rate and divide it by the temperature, and that's the rate at which entropy is either entering or leaving the control volume with the heat transfer. So that's pretty easy. And then we have a summation over I, the index of the mass flow rate entering at times the specific entropy entering. So, you simply, if you have one location where you've got mass entering, then you've got whatever that mass flow rate is times that specific entropy. If you've got 3 locations where they're entering, you have to treat each one separately. You have to know all 3 mass flow rates, and you have to know all 3 specific entropies, and you simply, put it together in the equation. So we got a similar term on the exits, minus the summation over E for exits of m dot exiting times the specific entropy exiting. And, you just, if you got 1, the summation turns into just 1 term. If you got 10, then you've got 10 different mass flow rates in, 10 different specific entropies in. It's a little perspiration, but it's not particularly hard. You just have to hopefully have all that information at hand. And then we have the rate of entropy production term, which is from irreversibilities that occur within the control volume. When I say irreversibility, you should think friction, turbulence, dissipative effects. That's what we mean. That stuff, it only goes one way. Okay? And so if we're assuming ideal reversible conditions internally in our system, then we don't produce any entropy in the system. But no real system exists that doesn't have these dissipative effects. So any real system is going to have some entropy production associated with it. Okay? And that's really about it as far as the entropy rate balance equation is concerned. That's 634, I guess, in your text. And then, we look at the special cases. How can we simplify? Well, if we say those golden words, steady state, when you hear steady state, your life just got easier because the transient problems are harder. They just are. You've got more things to consider. You've got time rates changing and stuff like that. But so if it's steady state, you get to set the dSCV dt term equal to 0. And so then you've got all the other stuff on the right-hand side of the equation as already described. Okay? And then for many, many practical components, simple turbines, pumps, compressors, nozzles, diffusers, all that stuff. We oftentimes have 1 inlet and 1 exit.
He'll probably talk about it more
for the. I'm sorry?
All right. Okay, so let's see here.
Okay.
I labeled my points differently than even he did.
Okay. Oh, it's not even in these. It's in.
I labeled it the same way as what was labeled on the homework, just so I could keep things straight.
Okay, let's.
Take care of that. I didn't hear did he have a question? He was just talking? Okay. Sorry, Casey. Where was I? Okay, well, so for all these fairly common devices, 1 inlet, 1 exit, then the summations go away. And if it's steady state, you got the same mass flow in and the same mass flow out. And so you just have 1 mass flow, so you can factor it. And so you get the mass flow rate times S1 minus S2 plus production, plus the summation of the heat transfers over the temperatures. There you go. Simplifies down pretty nice. Okay, so let's do a little example here. So we got some water vapor, we got some steam, and it enters a valve at 0.7 bar and 280 degree centigrade, Celsius, and exits at 0.35 bar. So we're dropping pressure, dropping it in half, I guess. If the water vapor undergoes a throttling process, determine the rate of entropy production within the valve in kilojoules per kilogram. Kilojoules per K, which is entropy, per kilogram of water vapor flowing. So that would be the specific entropy production. And B, what is the source of the entropy production in this case? Okay, so we got a little picture over there, And, you know, it's just a throttling process. And so you see that down here, you see H2 is equal to H1. So if you remember the throttling process is my favorite process. It's the one that the first law, when you throw out kinetic and potential energy changes and you do steady state and you throw out the heat transfer, you wind up with H1 is equal to H2 or H2 is equal to H1. The enthalpy doesn't change across that valve after you make all those assumptions. And so when you hear throttling, that's the one you ought to remember, enthalpy is constant. I mean, assuming that they haven't stuck a little heat transfer term in on, you know, or they're doing something nasty with kinetic potential energy changes. But generally speaking, when we see a throttling valve, we just assume enthalpy is constant across it. So that's kind of handy. Okay. And he just goes ahead and writes that down because we're in chapter 6 and we talked about that in chapter 4. So you're now experts on chapter 4 because we're in chapter 6. These guys that write the book, that's the way they think, right? Okay. So we look at the second law for steady state. And, you know, for a single inlet, single outlet, it just boils down to that. That's all the terms. And then, of course, no significant heat transfer. So the summation of the Q's goes away. So we wind up with that. And so there you go. So, you know, we just took the, it's S1 minus S2. So and then we divide through by m dot. So we take that term to the other side of the equation. Whoops. And it becomes S2 minus S1. So that's why the sign switched. We just took it to the other side of the equation. Divided through by m dot. It's pretty easy. And then we go to the tables and start looking up stuff. So state 1 is just a direct lookup from the tables. And what was that? That's 0.7 bar and 280 degrees C. If you have any question, it wouldn't be bad to go out on your own and verify. Make sure that you see the same numbers that they do. But you should look up a table, information from the table, H1, 3035 kilojoules per kilogram, and S1, 8.3162 kilojoules per kilogram per degree K. Okay, for a throttling process, H1 is equal to H2. Now here's where these things, they're not hard, but they're a pain in the rear because you always have to interpolate for the second state. So as we go into this test, you need to dust off your interpolation skills. You know, so this would be a good opportunity to go do the interpolation in the table and make sure, 1, that you're clear on how to do it, and 2, that you can do it quickly. Because if I give you 12 problems on a test with 80 minutes, you're not going to have time to re-teach yourself how to interpolate. If you do, pardon the expression, but you're going to be screwed because you're only going to get through half of the test. You know, that's on you. At this point, you're supposed to know how to interpolate, okay? All right, so anyway, because see, what you know about state 2 is you know the pressure and you know the enthalpy. Well, guess what? When you know the pressure, hopefully you can find, you know, in the tables 0.35 bar, right? But you're not going to find that exact enthalpy, most likely. It's very unlikely. So you're going to have to take that 3035 into the tables at 0.35 bar and interpolate in order to determine what that entropy is. So anyway, that's just the way it works. Okay, and so just plugging all this into our simple little equation, the production term, entropy rate of production for the control volume divided by the mass flow is equal to just the difference in those. So it's positive 0.3133 kilojoules per kilogram per degree K. So what's that tell you about what's going on inside the control volume? Is it reversible, irreversible, or impossible? Well, it's not impossible because entropy increased. It's not irreversible. I mean, it's not reversible because entropy increased. So we have irreversibilities present in the control volume. That's what that tells you. And it's possible for this process to proceed, to happen. Okay. And then if you go back and look at section 531, they list all of the different types of irreversibilities: friction, unrestrained expansion to lower pressure. And there's a whole list in there. I can't remember everything off the top of my head that they list, but there's a bunch of stuff. And so, you know, this one would fall under the category unrestrained expansion to a lower pressure. Because once you go to that lower pressure, you can't blow a magic whistle and get it to run back upstream to a higher pressure. You know, there's nothing in an energy balance that would preclude that, but it's not going to happen, you know, and that's the second law aspect of it. Okay, comment, and this is pretty good. Every once in a while, the author rolls in some discussion here that I really like, and I kind of like this one. So we'll read it here. The value of the entropy production for a single component, such as a throttling valve, considered here, often doesn't have much significance by itself. The significance of the entropy production of any component is normally determined through comparison with the entropy production values of other components that combine to make up an integrated system. So, you know, like we have throttling valves in refrigeration systems. You know, so we have a compressor, we have a heat exchanger called a condenser. We go through a throttling valve to drop pressure. And when we drop pressure on that refrigerant, it gets really, really cold. And then we put that through another heat exchanger, we blow air across it, and we get air conditioning out of it. And that then boils off any liquid, and we get superheated, and we go back in the compressor, we go around and around and around and around in a cycle. Okay, so if you're looking at this cycle and you're trying to make it more efficient, you want to know which component has the most irreversibilities present, because that's the one that gives you the most opportunity for improvement. And so, you know, so if you were working for Trane or Carrier or something, working on one of their air conditioning systems, you might well go through each one of the components and calculate the irreversibilities, the entropy production by each component, and then say, oh, wow, oh man, look at this compressor, oh my God, this is 10 times more than anything else in the whole system. So what are you going to try to optimize first? Well, you're going to go to that component because that's the one that's producing the most irreversibilities. And so if you could cut those in half by some eureka moment, some new compressor comes on the market or whatever, and it's umpteen times more efficient, you go, wow, that's the component I need to be looking at. Is it the heat exchanger? Is it the throttling valve? You know, where can I get the most bang for the buck in terms of trying to optimize this cycle? So that's where this stuff really picks up a lot of its value in terms of practical engineering applications. Okay, so calculating entropy change. Well, my goodness, what do we got there? The old TDS relations. And he got the sign right on the second one. I eventually got the sign right after we edited them all in class last time, but at any rate, so the property data provided in all those tables, A2 through A18, similar computations for other substances and numerous important relations among such properties established using the TDS equation. So, I mean, we developed these in detail last time, so I'm going to skirt through this pretty quick, but they're just ubiquitous. Those little rascals show up all over the place in thermodynamics. And so 610A and B are written for a unit mass. So we've got the specific values of entropy, internal energy, specific volume, and enthalpy, but you've seen those before. So as an application, consider a change in phase from saturated liquid to saturated vapor at constant pressure. So this was the old piston cylinder, you know. I mean, I think early on in the course, I told you, you're going to hear about so many different piston cylinders because that's the main component we use in describing all of this stuff. The frictionless, you know, piston that runs up and down so we can do something at constant pressure. So, you know, I think last class we were doing it from vapor, we were condensing. In this discussion, we're going to go from saturated liquid to saturated vapor. And we've got the sliding blue dot here, which of course is always exciting to see. We can go back and forth and watch it again. So we're going to go from the saturated fluid F or liquid to the saturated vapor or gas and consider it. So since pressure is constant, the energy rate, or not the energy, but the entropy balance reduces to give ds is equal to dH over T. And remember, the dH is because that's a du plus pdv, and the pressure is constant. And when you've got an expansion, you know, like this, and a change in internal energy, all those terms combine to give you the dH. So you should know that by now. We've been through it a number of times, but please note that. Because this expression, really, if you multiply through by the T, is TdS is equal to dQ. But from the first law, say they just expect you now to do all this in your head, you know, because you got to control mass. And so it's what internal energy plus PDV is equal to Q. If you solve Q for the first law of energy balance for a closed mass, or dQ, then you get du plus PDV, and that is dH, and that gets substituted in here. So all that stuff has already gone on to get us to this point. Okay, and then we're just going to integrate it, and because we know temperature is constant as we go across the dome, then I can do the integral of ds is just, you know, basically S2 minus S1 or SG minus SF. And then I pull out a 1 over T and integrate DH, and I get H2 minus H1, which is HG minus HF. So there you go. And so this relationship is what's applied in the property tables. And I think we may have even done some of that last time too, but anyway. Okay, so let's look at another example. Consider water vapor at 100 degrees C. So that's at 100 degrees C, that's atmospheric pressure, right? Which is 373.15 Kelvin. And so you can just go to table A2 at 100 degrees C, and you look up this Hg minus Hf, which is the distance across the dome in terms of enthalpy coordinates. So it's the enthalpy at this point minus the enthalpy at this point. And so, you know, he wrote out the difference here in terms of Hg minus Hf. Sometimes we just call that HFG. So if you see H with a subscript FG, that's shorthand notation for this, and this is tabulated in the table. So they just, you know, in the tables, they'll do this subtraction for you and go ahead and tabulate it, which is nice. It keeps you from having to take the vapor enthalpy and subtract the liquid enthalpy from it. Whoops, okay. And so then he's just showing that if I take that HFG and divide it by the temperature in Kelvin, I get the entropy change, or SFG, GF, however you want to put the subscripts, is equal to 6.049. Calculated, and you go in the table, and guess what? It's 6.049. So just demonstrating how those tables get put together. Okay, so next, the TDS equations are applied to two additional cases. And we ran through these last time too, but I think hitting them again is pretty important. You know, what you're going to find when you start prepping for this test is when you get to chapter 6, you got a boatload of equations. You know, if I assume this, I get this. If I got an ideal gas with constant specific heats, I get this. If I get this, I get this, I get this. And so you really have to be clear. You know, you can write them out on a sheet, or, you know, it's open book, so, you know, you can look at them in your textbook, but you just have to be clear that you understand under what conditions I can use which equation. Okay. And, you know, you're just going to have to review it to the point that you become comfortable with it. But so we'll hit the incompressible substance and then the ideal gas situation again. So, you know, incompressible substance, liquid, typically water or something like that. Good assumption. Assumes that specific volume and density is constant. Specific internal energy depends solely on temperature. So U is a U of T. Thus, du is the specific heat of T times dt. And where C denotes specific heat. And there is just one. There is no CV and CP distinction for incompressible substances. Okay, so we stick this into our relations for entropy. And so this is the TDS. This is 610A, which is where's 610A? Right there, 610A. So TDS is du plus PDV. Okay, and so for du, we put in C of T dt over T, and because we're incompressible, the dV is 0, and so it simplifies to that. And then on integration, we would get this. And then if we're willing or able to assume a constant specific heat, then the temperature terms integrate into natural log of T2 over T1. So when you see these relations, you see these little parentheses things over there. Those are the conditions under which you can use that expression. You have to be assuming incompressibility, and you have to be assuming a constant C. So if you had a temperature range for that C, and you wanted to use that, because it's simple and easy, what you would do is if you have a table that gives C as a function of temperature, you take the average temperature, and then you evaluate the C right in the middle of the range, or you take the average C based on averaging your temperature. And that's about the best you can do. So if you have a small temperature range, then this will be pretty good. If I have a great big temperature range, because those specific heat functions really aren't linear, and over a big range, they move all over the place. We've got some curves of them in the appendices. So, you know, over a small temperature range, it's, you know, each little section of the curve is pretty close to a straight line. And so you get a pretty good average. But if this thing is moving all over the place, it's over a big temperature range, then this isn't going to work very well. Okay. And this is, so this is incompressibility. And now we're done with that. So we have that relation. And now we're going to move on to the ideal gas model. And remember, we made these assumptions. We used PV is equal to RT. We used the same thing for internal energy is a function of temperature, and enthalpy is a function of temperature. And we can substitute in these relations into the second TDS, or into both TDS relations. So that's why I put in all that other stuff, because this is what the author had in here. He just jumps to all of this, and I just think it's too important. I want to make sure that you know where it all comes from. Okay, so on the left, you know, we've got TDS du over T plus P over T dV. And then we're going to use this ideal gas law to substitute for P over T. But P over T is R over V. And so and then we substitute DH is CP dt. And so we get this. I'm sorry, it's du. I'm sorry, this one is du, so it's CV dt. And then we're going to integrate, okay? Well, we can integrate this term directly. We got the specific heat function in here. We got to figure out what we're going to do with it. So that's what that integrates into. And then on the other TDS relation, we simply make these substitutions. We've got a V over T. And so up here, V over T is R over P. So that goes in. And so we get this term R times dP over P, which we can integrate. And then we wind up with a specific heat Cp function in the integral. So you should be pretty good on that. We've been through it a couple of times. Okay, just to recall, you see these R's, that's not R hat. That's the specific gas constant, which is universal divided by molecular weight. We should be used to that. And we know CV and Cp are functions of temperature for ideal gases. So if we're going to really do this the best way we can, we need functions. And you have functions for these things in your appendices. In fact, one of the homework problems actually inserts one of those functions and does the integral. So, for several gases modeled as ideal gases, including air, CO2, CO, O2, and nitrogen, and water vapor, evaluation of entropy change can be reduced to a convenient tabular approach using this S superscript 0 as a function of temperature. So for these gases in this table, when you see these S superscript 0, they have done this detailed integration for you. So using this approach will get you a much better answer than assuming a constant specific heat and doing that integral into the log of T2 over T1 and just multiplying by that specific heat. So they define this as the specific heat at constant pressure as a function of temperature divided by temperature times dT. And they just pick a reference temperature. I don't even know if I know. They pick some convenient temperature. And then they go out and they perform all of these integrations and they tabulate this thing, okay? Because T prime is just arbitrary. It doesn't matter what they pick so long as they pick the same one every time, okay? And then what we do is say this integral term, T1 to T2 of Cp dt over T, then you can integrate from T prime to T2, do that integral, and subtract off the integral T prime to T1, and you wind up with this integral, which is what you want. And so that is little s superscript 0 at T2 minus little s superscript 0 at T1, and you just look up these values in the table. Oh my gosh, it can, I mean, you know, how nice, I mean, what a nice process. And this is going to give you very accurate results because they took, the good curve fits for CP, and they did this integration for you. Well, in one of the homework problems, you get to at least see doing the integration once, and you go, oh crap. I mean, I can do it, but I don't want to. And so all that's tabulated, so long as you have the right gas. That's where the rub can come in. If you're working for somebody and you're using some fairly, unusual gas, you're not going to find it tabulated, and you're going to be forced to do the integration yourself. So, welcome to the real world. It happens. Okay. So then when we plug this in to our expression for the entropy change for an ideal gas as a function of temperature and pressure, then for that first, for the temperature, the specific heat temperature integral, we just go look up the S superscript 0 at T2 minus S superscript 0 at T1 and subtract off the specific gas constant times the log of the pressure ratio. Just make sure you got absolute pressures and you're good to go. So that's really, really nice. Okay. For some of these gases, it may be listed on a molar basis instead of a a pound basis. So on a molar basis, you just have to realize you're getting the entropy change per unit mole instead of per pound. If you want it, or per mass, it could be kilogram or pound. So then you would just have to divide by the molecular weight to convert that. And the R then is the universal gas constant here times the natural log of the pressure ratio. So that's pretty good. Okay. So he's just talking about the tables that have the, and again, some of them are in terms of kilogram or pound, and others are in terms of moles. I guess A23 is in terms of moles, A22 is in terms of pounds. So you just have to be a little careful on the units. Okay, so let's do a little example of this. Let's see, so we want to do the change in specific entropy, units kilojoules per kilogram per degree K of air as an ideal gas undergoing a process from 300 Kelvin and 1 bar to 1420 Kelvin and 5 bar. This looks like a big time compression process. Okay, well, so here's a cut from table A22. So we see at 300K, and this superscript, that superscript 0 really indicates it's like a 0 pressure, because the pressure doesn't come into play here. We have a separate term that accounts for pressure. Okay, so you find 300K in the table. Look up S superscript 0, 1.70203. Come over to the 1420 Kelvin. We got 3.37901. And plug it in. So there's the numbers. And so this is the subtraction of those. This is the specific gas constant. So this is R bar divided by molecular weight. And this is a log of the pressures. And bingo, you do all the math, and you get 1.215 is the entropy change between those two states for that process. Okay, not too bad. Okay, these are our two new diagrams that we pick up. We pick up the TS diagram. We had these before. Just to look at them again, we have a saturation dome. These are lines of constant pressure, isobars. And these things kind of trail off down here in compressed liquid land, across the dome and up. And so this process line would show an isentropic turbine that we'll see. So if we went from 1 to 2, that's what an ideal turbine expansion would look like, because it occurs at constant entropy. So you can see from 1 to 2, there's no entropy increase. We can't go backwards because that would be an entropy decrease. A real turbine would actually come forward over here to the right and intersect this P2 isobar someplace up in here, like we're kind of showing over here on the Mollier diagram. And so if we went from 1 to 2, we get this. If we went on to 3, we get this. If we went from 2 to 3, we'd get this. But this is all isentropic, constant entropy. And isentropic is what? Adiabatic reversible, internally reversible. Those are our code words. Okay. And this shows on the Mollier diagram. This even has the turbine. This is jumping ahead. We'll talk about this here in just a few minutes. But anyway, so this would be an isentropic expansion from 1 to 2. This is what a real expansion looks like. You wind up at the same pressure, but you have an entropy increase because of the irreversibilities in the actual device. So Mollier, enthalpy versus entropy, and TS, temperature versus. And those are specific entropies. Okay, so let's see. This is looking at an isentropic process. So if this is just an ideal gas, or we're out here in the vapor away from a saturation dome, we get, you know, the point, say we're going from 1 to 2, a compression, we're going up in pressure. You know, this is a line of constant specific volume going through that point, line of constant temperature, and line of constant pressure. So we see the same kind of lines drawn through both states. So if it's isentropic, that means the entropy change is 0. So then we can take these expressions and we can use it to solve problems to find, you know, we basically have 1, 2, 3, 4 variables here, right? We've got T1, T2, P2, and P1. So if any 3 of them I know, I can find the 4th from this relation. So for example, if I know T1, P1, and P2, then I can write this, I can solve it for this term, S superscript 0 at T2, and then if I have a number for that, then I go in the tables and I interpolate to find the temperature, if that's what I'm looking for. So that's kind of the procedure. But that's obviously isentropic. Okay. Likewise, if you don't know P2, but you know the temperatures, then you simply solve the equation for P2. You plug in your numbers and you can calculate it directly. Okay, so for air modeled as an ideal gas, we have one more presentation of the data. So this is a very specific case. So this is air for an isentropic process for an ideal gas. You can use this, and this is really, really handy. Okay, so an alternate method is offered. So, you know, if we work on this a little bit using our mathematics, we can write P2 over P1 is the exponential of S superscript 0 at T2 divided by R, and that whole term divided by the exponential of S superscript 0 at T1 divided by R, okay? Well, guess what? This quantity is tabulated for you in the tables, and it's given the name P sub R of T. So you can go look up this, which means you're looking up this, which means that we can rewrite this expression as this. And, yeah, okay. So then, I mean, this was really handy. So, I mean, you just go look up this, and it's just a number to you, but this relationship holds for either an expansion, a compression process, whatever. So this would be P2 over P1 is equal to PR at T2 over PR at T1, but it's only if it's constant entropy and only for air, because this is only tabulated for air. You won't find it for any other gas. Okay. All right, and then we'll have an example here in a minute. And so they've also done this sort of thing for specific volumes and temperatures for 2 states having air. The same specific entropy can also be developed. So again, isentropic, air, ideal gas. So if you can write this ratio, V2 over V1, just apply the ideal gas and write it for V2, which we've done here, and then write it for V1 and flip it upside down because we're dividing. And so we can get that, but because it's isentropic and an ideal gas, where we have this, say we have this pressure ratio P1 over P2, well, I can substitute in PR of T1 over PR of T2, because that ratio is the same. And then this quantity is tabulated as V sub R of T. Okay, and these are, what do we get? They're called relative pressure and relative volumes. Okay, and both of those show up for air in tables A22 and A22E. So V1 over V2, or V2 over V1 is VR2 over VR1. Again, constant entropy and only for air. So those are actually pretty handy to use. Okay, so here's an example. So when the entropy S1 is equal to S2, the following equation relates the temperatures and pressures. Okay, so we just read them from the table. Well, let me go back. So whatever temperature that you have, you simply, for T1 and T2, you plug them in. And so, for example, if you wanted to know what P2 was, starting from P1, and you know the temperatures, then you can plug that in and solve very easily for P2. So just kind of a shortcut on some of these problems. Likewise, we can do it with the volumes. Okay. So that's the relative pressures and volumes. And now we're going to do some more simplifications to these relations that we already have. See, I mean, how many daggum equations do we have? I mean, we got equations running out of our ears. And so you really have to sit back and look at these and be comfortable with when do I use which relation? What assumptions am I making? Or you're just going to go nuts on this test because there's just too many equations out there. Okay, so we had 617, we've got our temperature integral here, and we got 618. This one has CV, this one has CP, but basically a similar integral. Well, okay, so if we make the assumption of constant specific heats, which we would love to do, then obviously the CV comes out and this integrates into log of T2 over T1. The CP comes out, we get the log of T2 over T1. And those are, pretty simple expressions to evaluate. But that's an ideal gas, and you've made the constant specific heat assumption to get there. Those things get used a lot. Particularly, they can be applied to develop relations among temperature, pressure, and specific volume at two states having the same specific entropy. Okay, so now we're going to take these. We're going to set the entropy change equal to 0, and then we're going to do some more math on them. So you're going to have a whole nother set of equations that you can use for ideal gas, constant specific heat, isentropic. All right, so there you go. S1 equals S2, we set them equal to 0. And don't forget, we also have this, where K is the specific heat ratio, CP over CV. One I remember, air, it's typically about 1.4, something like that. But anyway, so if you know the K and you know the specific gas constant, you can calculate CP and you can calculate CV. That's another good trick that you need to know. See, these are all little individual tricks that then you have to draw on different ones on a particular problem to work your way through to a solution. And so if you go through the math on this thing, so we can solve these equations to give that T2 over T1 is P2 over P1 raised to the K minus 1 over K, where that's specific heat ratio. Or T2 over T1 is specific volume 1 over specific volume 2 raised to the K minus 1. And you see the requirements, constant entropy and constant K. Well, you know specific heats change all over the place. So you're assuming that CP and CV are constant, and because that's what constant K implies. Or you can eliminate temperature, and you can get P2 over P1 is specific volume 1 over 2 raised to the K. So I think this is the end of the equations that we have to develop. And I don't know about you, my head's swimming in equations right now. You know, I'll be honest with you. Okay, so let's do some examples here. Air undergoes a process from 620 Kelvin and 12 bar to a final state where the entropy is equal, so isentropic, and the lower pressure is 1.4 bar. So we're going from a high pressure and high temperature to a low pressure. Employing the ideal gas model, determine the final temperature T2 in degrees K. Okay, so we're going to do it A using the relative pressure data, and then we'll do it with a constant specific heat ratio, K, evaluated from table A20, which is K is 1.374. And then we can look and see how that works for us. Okay, well, now this is going to be the most accurate way, right? Because the piece of R values, they have integrated those specific heat functions of temperature in order to develop this. So this, I mean, this is, you know, this is probably going to give the best answer. So we look up piece of R at 620 and it's 18.36. Well, that wasn't very hard. And so, and we know the pressures. So, I mean, look how simple this is. And you get a good answer. I mean, man, you should not shy away from using these relative pressures and specific volumes. So we take the 18.36 times the pressure ratio, you know, and solve that for PR2. And we get what, 2.142. And there we are. We're over there interpolating. You see, we've got 2.142 here. I've got 2.149, pretty darn close to 340, a little bit further away from 330. You do the interpolation, and you get 339.7 Kelvin. And that'll be a pretty good answer, okay? So that's one way to do it. Okay, we also had these relations. So this was what? Isentropic, ideal gas, constant specific heats, or constant K. So we had all three of those assumptions in order to allow us to use this. And so then we simply plug the numbers in that we have, and we get 345.5. Well, you know, that ain't just great. You know, it depends what you need. Hey boss, how accurate a temperature do you want? You know? And of course, the comment here is that the approach of A accounts for a variation of specific heat with temperatures, but the approach B does not. With a K value more representative of the temperature interval. So he's saying, okay, if you pick a better K value, then you'll get a better result. Well, maybe you already picked the best K value you know how to pick. I don't know. You know, where did you get it? You went in the tables and looked. You know, so, and, you know, so if you don't do the first, if you do the first, why are you going to bother doing the second? You know, because you've already got a good answer. But if you do the second first, you don't have anything to compare to. You don't know if you picked a good K or not, you know? So, I mean, my advice would be just do the first one. But, you know, for academic purposes, this just shows you what you know, what kind of agreement you're going to get between a more, the two different processes, I guess. Okay, let's get on to isentropic turbine efficiency. Okay, so this is one of the big uses, these isentropic devices. Okay, so before we do this slide, let's just kind of kick back for a second. And an isentropic efficiency, a general description, and I probably should put a couple slides in here for this. It's a comparison of a real device to an ideal device. Now, we're going to have turbines, we're going to have compressors, we're going to have pumps, we're going to have different devices. Okay. And so we want this efficiency to be a percent between 0 and 100. I mean, someplace in there, depending on however the number comes out. So for a turbine produces work, right? A pump and compressor require work. Okay, so let's talk about the turbine first. So it's going to be the comparison of an actual turbine to an ideal turbine, basically with the same inlet conditions and exit pressure. Okay, well, so just from a common sense point of view, is an ideal turbine going to produce more work than a real turbine? Well, heck yeah, it's ideal. I mean, that's kind of the definition of it. So when I form the ratio, I'm going to put the real work in the numerator and the ideal work in the denominator, because when I do the division, I'm going to get a number less than 1, and then I'm going to multiply it by 100, and I'm going to get a percent. Make sense? Okay. Now, think about a pump. A pump requires work. You put the work in. So, is a real pump going to require more or less work than an ideal pump? It's going to require more, right? Because an ideal is going to require the minimum. Okay, so when I form that ratio, you always put the big one on the bottom, right? Because I want that to be a fraction. So for a pump and a compressor, I put the isentropic work on top in the numerator, and I put the real work from the real device in the denominator, because I get a fraction less than 1, and then I multiply it by 100. Okay, so that's my tie rate. And so once you understand that, because you may be working on something, and once you see how easy it is to write these relations, you don't have to go look in the book to see which is on top, if you just understand the concepts. Okay, so let's go back to now the slides. For a turbine, the energy rate balance reduces too. And so this is going to be for steady state, right? It's steady state because you got a 0, what? On the left. And that's what? This is energy. So this is dE CV dt is set equal to 0. So that's the heat transfer rate, net heat transfer rate for the control volume, minus the net work done by the control volume, plus, and we only have one inlet and one exit here. So we've gone ahead and factored out m dot, and then it's times the enthalpy difference in minus out, the velocity difference squared in minus out divided by 2, and any elevation changes between 1 and 2, z1 minus z2 times the gravitational constant. So we should be good with that. Okay, well, typically with these turbines, we throw away kinetic energy changes. So V1 squared minus V2 squared, 0, disappears. We throw away kinetic energy. I'm sorry, potential energy. There's not much elevation difference. Term is trivial. Throw it out. Guess what? I like this. We just keep throwing out all the terms, right? This is the kind of analysis we like. In the fluid, the hot steam passes through a turbine so fast it doesn't have time to lose any energy. Plus, we insulate it. So you almost always throw away the heat transfer term. Well, that's pretty nice. So what do we have left? The work produced by the turbine per unit mass is just the enthalpy change. Okay? And H1 is going to be high temperature, high pressure. H2 is going to be low pressure, probably lower temperature. So H1 minus H2 is going to be plus. Okay? Now, the work term, this is the fluid doing work on the surroundings. So that's our definition of positive work. Okay? So we should expect W dot CV to be positive. Mass flow rate has to be positive, and H1 minus H2 is going to be positive. So there we go. We got our, we need to think through our signs and make sure we get all our conventions right. So that's the work developed per unit mass flowing through the turbine. Okay, now we go to the entropy rate balance. Again, steady state, dSCV dt set equal to 0. There's all of the possibilities. You know what those are now. We're adiabatic, so we don't have any Q's, so we throw out that term. So then we just rearrange this. So we take the divide through by m dot and take the S1 minus S2 to the other side of the equation, which flips the sign, so we got S2 minus S1. And so that's a production term per unit mass. So we know it can't be negative, right? Because the only way I can reduce entropy for a control volume, well, is in terms of the, I guess, the mass flows can do it, but I'm doing this per unit mass, is to have heat transfer, and I have disallowed heat transfer, so it's got to be positive. That's a production term. There we go. Okay, so how are we doing here time-wise? We got a few minutes. Okay, so if you look at a Mollier diagram, this is what you see. So enthalpy, entropy, P1, that's my high pressure and my high temperature coming in. So if I do this isentropically, I drop straight down. So then the way I find this state 2 and 2s, they put the s on there to remind you that it's isentropic. This is 2, some books call this 2a for actual, and some just call it 2. Here he's just calling it 2. But so this is what the actual turbine can do. This is what the isentropic turbine can do. Okay, and so you find this 2s point, you know a pressure and you know an entropy because you know your condition coming in. So you look up the entropy here, you apply that same entropy at this lower pressure, and guess what? You got to go interpolate in the tables. These isentropic things require a lot of interpolation. Sorry. And then for state 2, you have to be given information because that's the performance of a real turbine. You don't have any real way to predict that except for information given in the problem. And so that's what it looks like. And so, see, we get a different enthalpy. You see, the enthalpy difference from 1 to 2s is greater than the enthalpy difference from 1 to 2. Because some of this extra enthalpy goes into the dissipative effects, the friction and all that other crap gets eaten up by that, okay? And so the other comment is you come straight down here at constant entropy. All these states back to the left are impossible because that would require an entropy decrease through this control volume, which is not possible. Okay? So I guess we can look through this. Pretty much what I said. 2s is obtained only by an isentropic expansion, adiabatic, internally reversible. From the inlet state to the specified exit pressure, 2s would be attained only in the absence of internal irreversibilities. So the maximum theoretical value for the turbine work, and that's what W dot CV, this little s means it's isentropic, is H1. So we have the same entering point for both turbines, same temperature and pressure, but so we got H1 minus H2s. So I have to find the enthalpy down here, and that's the theoretical max that we could do. Okay? Then we determine the actual work out of the turbine, the W dot CV over M dot, the M dot's the same, for the real turbine. So we have to have information that lets us find this enthalpy. And so we get H1 minus H2, which is the actual turbine, divided by H1 minus H2s, which is the ideal or the isentropic turbine. There you go. And there's your ratio. Multiply it by 100 and you get a percent if you want. And that's the way we do it. Okay. So let's look at an example of this. Water vapor enters a turbine at 5 bar and 320 C, exits at 1 bar. The work developed is measured as 271 kilojoules per kilogram of water vapor flowing. So see, that's the actual. See, so somehow you got to be given information where you can determine, so that's the actual work. So that's H1 minus H2. He's just giving it to you in this one. Other times they may give you a temperature and a pressure. I mean, you know the exit pressure. So if you know a temperature, then you can go find that enthalpy in the tables. But somehow you got to come up. Now the isentropic, you know, you get from the entropy and the pressure. Okay. So from table 4A, so there's H1 is just a lookup. So we use that for both turbines. And S1 is 7.5308 kilojoules per kilogram. Ah, there's a mistake. This is his slide. There should be a degree K after that. So there's a unit error there. S2S equals S1. Interpolation, table A4 at a pressure of 1 bar gives, so you've gone to the table, you've interpolated with this entropy at the lower pressure, and you get 2743 kilojoules per kilogram, and then we just substitute those in. So the 271 is this entering minus exiting for the actual. They gave you that. So this is for the isentropic, and we get 0.75 or 75% efficiency. Okay. I think we mentioned earlier that when we were talking about first law on turbines, if you do just the energy balance around the turbine, the efficiency comes out, the first law efficiency comes out 99.8% every time, because they don't hardly have any losses, you know. But so it doesn't do you any good. I mean, it's meaningless to calculate an efficiency that always comes out 99.78, whatever. They don't change very much. But this is a meaningful number that we can use to actually figure out, if we're designing and building a turbine, how good is it? Well, let's compare it. You can't compare it to 100% because that's not fair, but you can compare it to an ideal unit. And so, well, we're 75% of what a perfect, a turbine with no irreversibilities, it's internally reversible, would be able to do. Okay, let's just, we'll do this one. Yeah, we'll do this one and then we'll quit here. We're just about through the slides. So next time will be pretty much just working problems. We might have a few to do. Okay, isentropic compressor and pump efficiencies. So we got the same first law we start with. Single inlet, single outlet. Bingo. We typically throw away kinetic energy, potential energy, heat transfer. There we go again. So, well, we pretty much got the same, we got the same situation. So H2, so let's say this is an air compressor. So what, the air comes in cool and low pressure. It goes out hot and high pressure. So the enthalpy at 2 is clearly going to be greater than the enthalpy at 1. Okay? So H2 minus H1 is going to be positive. That should be clear. Well, and so when we solve for this thing, we say we got the negative of the work of the control volume. Well, if H2 minus H1 is positive, that other term's got to be positive, which means the work term has to be negative to then interact with that negative sign and turn it positive. And so does that make sense? Well, we have a motor or something turning a pump. We're putting work into the fluid. So yes, that work by definition is negative. And so those two signs will turn the left-hand side positive. Okay, let's go ahead and stop. Y'all are getting that glazed look. All right, so we'll go ahead and we'll finish up. We don't have very many slides to go, and then we'll just kick back and work through some problems next time, and then we got the test on Thursday. So, and I will be sending you more problems over the weekend to look over to finish up this chapter. You guys have a great rest of the day, and I guess we'll see you on Tuesday.